If your goal is to build muscle, you're probably already paying attention to your training intensity, your protein intake, your sleep duration, maybe even your supplementation. But what if I told you there's one thing, just one simple behavior you can do before bed that acts as a kind of multiplier for all of that effort? And it's not a supplement. It's not a specific exercise. It's not a piece of expensive equipment. It's a neural and behavioral protocol you engage in the hour before sleep that directly impacts your body's ability to recover, build, and grow muscle tissue during the night. Specifically, it's about stimulating parasympathetic tone while simultaneously priming your endocrine system for optimal anabolic activity. Let me explain. The autonomic nervous system is divided into two branches. The sympathetic branch is often referred to as the fight or flight system, while the parasympathetic is known as the rest and digest system. For optimal muscle growth, especially during sleep, it's essential to shift the body from a sympathetic dominant state, often induced by stress, stimulation, or late night activity, into a parasympathetic state before bedtime. This transition plays a crucial role in enabling the body to access deep stages of sleep, particularly slow wave sleep, which is where the majority of physical recovery and muscle repair occurs. In a sympathetic state, cortisol and adrenaline levels remain elevated, heart rate stays higher, and the brain continues to process stimuli with a heightened sense of alertness. This is counterproductive to the hormonal environment needed for recovery, especially the release of growth hormone and the orchestration of anabolic processes. When the parasympathetic system is activated, heart rate slows down, breathing becomes deeper and more regular, and muscle tension decreases. This sets the stage for the hypothalamus and pituitary gland to coordinate the hormonal cascades that promote tissue growth and repair. The vagus nerve plays a central role in this shift. It serves as a major conduit of parasympathetic signaling and is responsive to various behavioral and environmental inputs. Techniques that stimulate vagal tone, such as diaphragmatic breathing, prolonged exhales, or even humming, can accelerate the shift into parasympathetic dominance. The act of slowing the breath to a rate of 5 to 6 breaths per minute with longer exhalations than inhalations has been shown to activate vagal tone and reduce sympathetic arousal. From a practical standpoint, that means deliberately disengaging from activities that stimulate the sympathetic system in the evening. These include consuming stimulating content, engaging in competitive or emotionally charged conversations, intense exercise within 2 hours of sleep, or exposure to high levels of light, particularly blue light. Instead, shifting toward behaviors that tell the body it's safe and time to rest. Things like lowering the lights, engaging in low stimulation movement like yin yoga, or even just lying quietly in a dark room can begin that nervous system transition. The body is exquisitely sensitive to environmental cues. And when those cues reinforce the message of safety and calm, the autonomic system adjusts accordingly. This shift isn't just about comfort or relaxation. It's about giving the brain and body the conditions needed to initiate the hormonal rhythms that govern growth and repair. The pre-sleep window is therefore a strategic opportunity to influence the body's recovery state through neurobiology. If the nervous system remains in a sympathetic tone, even partially, the architecture of sleep is altered. Cortisol remains elevated, reducing the amplitude and frequency of slow-wave sleep, thereby impairing growth hormone release. But when the parasympathetic system takes over, the transition into deep sleep becomes more efficient, hormonal pulses are stronger, and muscle recovery is optimized on a cellular level through increased protein synthesis, improved insulin sensitivity, and mitochondrial repair mechanisms. Light is one of the most powerful regulators of our circadian rhythm, and its influence on sleep quality, hormone release, and ultimately muscle growth cannot be overstated. In particular, exposure to bright artificial light, especially in the blue spectrum during the evening hours, can profoundly disrupt the body's ability to transition into deep anabolic sleep. The retina contains specialized photoreceptors called intrinsically photosensitive retinal ganglion cells, or IPRGCs, which are not involved in vision, but instead send light information directly to the brain's master clock located in the suprachiasmatic nucleus of the hypothalamus. When these cells detect bright light, especially in the blue wavelength around 460 to 480 nanometers, they signal the brain that it is daytime, suppressing the release of melatonin and resetting the circadian clock forward. Melatonin is not merely a sleep hormone. It plays a critical role in signaling the onset of biological nighttime, during which growth hormone is released in its highest pulses. When melatonin release is suppressed or delayed due to light exposure, the downstream effects include reduced duration and quality of slow-wave sleep, diminished growth hormone output, and a disrupted anabolic environment. Muscle repair and growth processes are most active during deep non-REM sleep, and those stages depend on the synchronization of melatonin, core body temperature rhythms, and parasympathetic nervous system dominance. Artificial light in the evening desynchronizes these systems. Sources of disruptive light include overhead LED lighting, computer screens, smartphones, televisions, and other electronic devices that emit high levels of blue light. The body does not distinguish well between sunlight and artificial light in terms of its circadian impact. So even brief exposure to a brightly lit screen can delay melatonin secretion by hours. This leads to shallower sleep, fragmented cycles, and a hormonal profile that favors catabolism over anabolism. To protect the integrity of the sleep-growth relationship, it is essential to reduce light exposure in the 60 to 90 minutes before bed. This can be achieved through environmental adjustments, such as dimming household lights, switching to red or amber bulbs, or wearing blue light mucling glasses that filter out high energy wavelength. In parallel, using software that shifts screen light to warmer tones in the evening can also reduce retinal stimulation. These changes send clear signals to the hypothalamus that night is approaching, reinforcing the circadian rhythm and preparing the hormonal environment for rest, recovery, and tissue rebuild. The goal is not just to fall asleep faster, but to create the physiological conditions for deep, uninterrupted, slow-wave sleep, which is when satellite cells are activated, protein synthesis is initiated, and muscular microtears from training are repaired. Avoiding artificial light before bed is a high-leverage behavioral tool because it targets the central biological clock that regulates almost every system involved in recovery, from metabolism to endocrine function to neural repair. By aligning external light exposure with internal biological timing, the body is better able to generate the hormonal pulses necessary for nighttime muscle regeneration. This synchronization also improves the consistency and depth of sleep cycles, which further enhances the capacity for muscular hypertrophy through improved gene expression related to anabolic pathways. Engaging in non-stimulating activities in the hour leading up to sleep is one of the most effective ways to cue the body and brain for recovery, specifically for the physiological processes associated with muscle growth. The final 60 minutes before bed serve as a crucial transition period where the nervous system should gradually downshift into parasympathetic dominance. Activities like light stretching, meditation, and journaling have been shown to reduce sympathetic nervous system activity and foster a state of relaxation that supports the onset of high-quality sleep. Light stretching, particularly modalities such as static holds or gentle mobility routines, helps release physical tension that accumulates throughout the day. This physical relaxation signals the brain that the environment is safe, promoting the release of neurotransmitters like GABA, which reduce neuronal excitability. Reducing muscular tension through stretching has downstream effects on heart rate variability, respiratory rhythm, and cortisol levels, all of which are linked to improved sleep quality and the conditions needed for anabolic hormone release. Meditation, especially mindfulness or breath-flunked practices, activates the prefrontal cortex while simultaneously calming the limbic system, which includes the amygdala, a region involved in processing stress and emotional reactivity. By focusing attention inward and maintaining a state of non-judgmental awareness, individuals can shift their mental state away from the external stimuli and cognitive demands that often keep the brain in a heightened alert state late into the evening. This downregulation of cognitive activity helps facilitate the transition into non-REM sleep, where the deepest stages of physical recovery take place. It also has an impact on the autonomic nervous system by increasing vagal tone and enhancing heart rate variability, both markers of recovery readiness. Journaling, particularly when focused on structured reflection such as gratitude listing or clearing mental clutter, can offload cognitive tension and reduce nighttime rumination. When the brain perceives that unfinished tasks, emotional concerns, or unresolved thoughts have been externalized onto paper, it becomes easier to disengage from them, reducing the frequency of nighttime awakenings and improving sleep continuity. Better sleep continuity directly correlates with more time spent in slow-wave sleep stages, which are essential for muscle protein synthesis and the release of growth hormone pulses. The consistency of performing these low-stimulation activities night after night also strengthens behavioral conditioning. Over time, the brain begins to associate these behaviors with the approach of sleep, creating a predictable neurochemical environment in which melatonin, serotonin, and growth hormone operate in concert. This association becomes a powerful circadian anchor, reinforcing the sleep-wake cycle and amplifying the body's ability to adapt to training stress. Incorporating such activities into a pre-sleep routine creates a physiological and psychological bridge between the high-intensity demands of the day and the recovery-dependent needs of the night. They buffer the nervous system from overstimulation and create the neurochemical and hormonal landscape required for high quality sleep, which remains one of the most critical windows for recovery, muscle hypertrophy, and overall athletic adaptation. The presence of stimulants in the body, particularly in the hours leading up to sleep, can significantly impair the biological processes necessary for muscle growth and recovery. Caffeine, digital screens, emotionally charged conversations, and loud or high-tempo music all contribute to sympathetic nervous system activation, which is incompatible with the parasympathetic state required for deep restorative sleep. Caffeine, the most widely consumed psychoactive compound in the world, exerts its effects by blocking adenosine receptors in the brain. Adenosine is a neuromodulator that builds up throughout the day, increasing the drive for sleep. When caffeine blocks these receptors, it reduces perceived sleep pressure and elevates alertness, heart rate, and cortisol levels. Even when consumed as early as 6 hours before bedtime, caffeine can reduce total sleep time, delay the onset of deep sleep stages, and fragment sleep cycles, all of which impair the anabolic processes that occur during sleep. Alongside chemical stimulants, behavioral stimulation from screens, such as those on phones, tablets, or televisions, has a dual effect. First, they emit blue light that suppresses melatonin production through direct activation of retinal ganglion cells, as previously discussed. But equally important is the cognitive stimulation they provide. Content that is fast-paced, emotionally charged, or highly interactive keeps the brain in a heightened state of arousal, making it more difficult to transition into sleep. This elevated neural activity delays the descent into non-REM sleep and blunts the depth and duration of slow wave stages, which are critical windows for growth hormone release and protein synthesis. Conversations or social interactions that are emotionally intense can have a similar effect. When arguments, difficult discussions, or even highly stimulating topics are engaged with late in the evening, they can raise cortisol levels, increase heart rate, and cause the mind to ruminate well into the night. The sympathetic nervous system becomes engaged, leading to elevated stress hormones, reduced melatonin secretion, and poor sleep quality. Similarly, listening to fast-paced music or loud audio content before bed can activate the reticular activating system in the brainstem, increasing arousal and delaying the transition to restorative brainwave patterns. All of these factors, when occurring in the evening, send conflicting signals to the body about what time it is. The internal biological clock becomes misaligned with external behaviors, disrupting the circadian rhythm and the hormonal cascades that are synchronized to it. The suppression of deep sleep stages caused by stimulant exposure reduces the amplitude of growth hormone pulses, weakens testosterone cycling, and diminishes the efficiency of protein turnover, ultimately compromising muscular adaptation from training. Avoiding stimulants in the final hour, or preferably 2 hours before bed, is not only about falling asleep more quickly, but about optimizing the hormonal, neurological, and muscular recovery processes that depend on deep, continuous sleep. By eliminating inputs that activate the sympathetic nervous system and instead reinforcing behaviors that encourage a drop in arousal levels, the body is better able to transition into the anabolic state that governs nighttime muscle repair and regeneration. Maintaining a consistent sleep schedule is one of the most impactful yet often overlooked factors in optimizing muscle growth and recovery. The human body operates on a 24-hour internal timing system called the circadian rhythm, which regulates a wide range of biological processes, including hormone secretion, body temperature, metabolism, and sleep-wake cycles. When sleep and wake times are irregular, this internal rhythm becomes desynchronized, leading to disrupted hormone patterns, impaired recovery, and reduced muscle protein synthesis. Growth hormone, which plays a central role in muscle repair and hypertrophy, is released in its most concentrated pulses during the first phase of deep non-REM sleep, typically occurring within the first 90 minutes after falling asleep. This release is tightly linked to the timing of sleep onset and follows a predictable circadian pattern. If bedtime is inconsistent, the window for growth hormone secretion can shift or weaken, resulting in less efficient repair of muscle fibers damaged during training. Similarly, testosterone, another critical anabolic hormone, follows a diurnal rhythm, with peak levels occurring in the early morning hours, shortly before waking. Disruptions in sleep timing can reduce testosterone production or flatten its daily peak, undermining its ability to support muscle growth, recovery, and strength adaptation. These hormones do not operate in isolation. They are part of a complex, interconnected endocrine system that relies on precise timing to coordinate cellular processes that support muscular development. Irregular sleep patterns introduce biological noise into this system, weakening the signals that tell the body it's time to initiate tissue repair, glycogen replenishment, and inflammation control. Consistency in sleep and wake times allows the body to anticipate when rest and activity will occur, improving the efficiency of physiological transitions between states of alertness and recovery. The result is more robust hormone release, more predictable nervous system shifts, and enhanced sleep architecture, particularly the deep stages that are most critical for muscle recovery. Beyond hormonal factors, a regular sleep schedule also improves the structure of sleep itself. The body learns to enter deeper sleep stages more quickly and remain in them for longer durations. This increases the total amount of time spent in slow-wave sleep, where protein synthesis, immune regulation, and cellular repair are most active. Consistent timing also reinforces the body's ability to initiate autophagy, the internal process of clearing damaged cellular components, which is vital for muscle maintenance and growth. Additionally, stable sleep schedules align with temperature regulation cycles that influence sleep onset and quality. The body temperature naturally drops at night as a signal for sleep initiation. If sleep timing is erratic, the coordination between temperature drop and melatonin release becomes mismatched, making it harder to fall asleep and stay asleep. This misalignment leads to shallower sleep, more frequent awakenings, and impaired recovery capacity. In athletes and individuals engaging in resistance training, irregular sleep schedules have been correlated with increased muscle soreness, slower recovery between sessions, and diminished training adaptations over time. Over weeks and months, even small inconsistencies in sleep timing can add up to significant deficits in muscle hypertrophy, performance, and resilience against training-induced stressors. Lowering core body temperature slightly before bed is one of the most reliable physiological triggers for initiating sleep, and this mechanism is directly tied to the hormonal and neurological processes that enable muscle recovery and growth during the night. The human body follows a predictable thermoregulatory rhythm throughout the day, with core temperature peaking in the late afternoon and gradually declining in the evening. This drop in temperature is a natural signal to the brain that it's time to initiate sleep. The preoptic area of the hypothalamus, which governs sleep onset, is highly sensitive to changes in core temperature. When the brain senses a decrease in internal heat, it begins shifting the body toward parasympathetic dominance, slows metabolic activity, and initiates the release of sleep-promoting hormones like melatonin. These same conditions also optimize the release of growth hormone, which is secreted in pulses during deep non-REM sleep and is essential for muscle tissue repair, amino acid transport, and the activation of satellite cells involved in hypertrophy. One effective strategy to promote this cooling effect is to take a warm shower or bath roughly 60 to 90 minutes before bedtime. Although it may seem counterintuitive, the warmth of the water causes peripheral vasodilation and expansion of blood vessels near the skin surface, which allows heat to escape more efficiently once the body exits the warm environment. This heat loss creates a rebound cooling effect, lowering core temperature and signaling the brain that the body is ready to sleep. This temperature-driven trigger supports the body's natural circadian drop in thermoregulation and accelerates the transition into sleep. During sleep, a lower core temperature is maintained, particularly in the early part of the night, to facilitate deep, slow-wave sleep. This is the phase during which muscle recovery processes are most active. Deep sleep enhances protein synthesis, improves glucose metabolism in muscle cells, and reduces inflammatory markers, all of which are critical for muscular repair and adaptation following resistance training or other forms of physical exertion. Additionally, lowering room temperature in the sleep environment can further enhance this effect. Research suggests that sleeping in a room between 16 to 19 degrees Celsius, 60 to 67 degrees Fahrenheit, is optimal for maintaining the ideal core to skin temperature gradient. This gradient helps sustain deeper and more continuous sleep cycles. A cooler environment also minimizes nighttime awakenings, which can otherwise fragment sleep and disrupt the release of anabolic hormones that follow a time-sensitive circadian rhythm. Wearing breathable clothing, using cooling fabrics, and avoiding heavy blankets can also support thermoregulation. Beyond the physical benefits, a cooler internal temperature before bed has been associated with reduced anxiety and improved sleep latency, both of which contribute to a faster descent into restorative sleep stages. This connection between thermoregulation and recovery is deeply rooted in evolutionary biology, as the body has long associated lower nighttime temperatures with rest and safety. By consciously manipulating external and internal temperature cues, individuals can create a physiological context that enhances sleep depth, duration, and hormonal efficiency in a way that maximizes muscle growth overnight through improved recovery and cellular regeneration.